Okay, can you, is my screen visible?
Yes, sir.
So, we are here to discuss about some basics of this NPTEL course, Computational Fluid Dynamics. So, excuse me. So, basically, here we will be helping you to practice some of practice, give a practice for your assignments. Actually, these interaction sections will be running in parallel. There will be few more TAs. So, basically, for every week, the content for every TS will be more or less same. So this is for the first week. I think you might have been gone through the uh, first week videos and also the assignment as well. So let us begin. So basically, I'm here just giving an overview of the course or CFD as well. So CFD is a method by which we can solve this complex fluid mechanics problem, or we can find some what solution for a complex fluid mechanics problem without running the experiments actually. So doing experiments will be somewhat costly, and also in sometimes it will be difficult. And also suppose we have to do the experiments again and again, and also in different areas in geometrically distinct spaces, it will be difficult for us to create the exact environment. So suppose we are doing some experience in far western countries or somewhere, and the climate and the weather there will be entirely different than here. So even we are being so cautious about creating an similar environment, uh, there can be some discrepancies can creep in. So in CFD, we are running inside a computer, or it's entirely a computational thing. So the foremost advantage of the thing is it's like we are doing the experiments. CFD or such things are called numerical experiments, and we are doing it in an entirely clean environment. So that's what CFD is. So this is our first question. So here, can you can also read the question, please. You wish to improve the performance of an air-to-air heat exchanger by designing a better intake manifold because the cold airflow is not uniformly distributed across the heat exchanger. You wish to study this using CFD and arrive at a better design. For this problem, which of the following statement is true? Or is it? Sorry. Uh, am I clearly audible to everybody? One second, I got a comment that my voice is low. Okay. So, uh, in this problem, what do you think? Our options are: you expect CFD to give a reasonably correct solution. You expect the CFD would not be of much use. You would look for an analytical solution. You would rather do experiments. So here there are some things you might have learned from the course itself, from the first week videos itself. So CFD basically is an approximation. So we are approximating uh, the fluid mechanics equations, or the our basic fluid mechanics equations representing the problem. We are actually approximating that. We are more or less approximating to some reasonable accuracy. So if you are going to look for an analytical solution, so you might have uh, studied in the fluid mechanics course and all, the Navier-Stokes equation or the momentum equation as well as such. We can be we cannot get an analytical solution as such, and also it is kind of most cumbersome. Uh, Here in this particular case, it is for an air-to-air heat exchanger, and we are taking an intake manifold. So the problem is well known, or it's a well thought about problem. Uh, it's been done for many years. So like we will be having the basic properties of the here the fluid is air and also design intake. So we have the design properties or all the geometry of the uh, intake manifold is available. So we don't have to do the experiments again and again. It will cost us uh, a lot of money, also the time. So here we can expect the CFD to give a reasonably correct solution. So why it is called reasonably correct? Because I also already told you the CFD is an approximation, and also we can fiddle with the accuracy. So by choosing different schemes and all such things, we can go for better accuracy also. So here the solution is A. Uh, so our next question: we wish to solve for a steady state temperature distribution in a rod of length L, and the variation is only axial, that is one dimensional. Which of the following boundary condition combination is admissible? So here, what we are we have is we have a rod of length L, and we are only considering the axial variation of the temperature. And the question is which of the following boundary condition combination is admissible? So here, you might have learned from the first week videos that we will be having a domain or the volume or area where we have to find the velocity distribution or the temperature distribution. So that domain here is a one-dimensional one single rod, and the variation of the quantity or the parameter which we are interested is it is given that it is one-dimensional, that it is varying in one dimension only. So which of the boundary conditions are possible? It's the question. So suppose this is a rod. Uh, Here temperature at both ends. First, the thing is temperature at both ends. Then heat flux at both ends. Heat flux meaning what? Some Q at both ends. Then third is heat flux and temperature at one end. Then the fourth option is heat flux at one end and temperature at the other end. So the uh, admissible variation or the boundary condition. Boundary condition is the proper is from where we are taking the initial parameters or the boundary values for the parameter actually. So the here heat flux. Suppose heat flux at both ends cannot be taken. Uh, So, uh, this is- okay, so here heat flux, actually heat flux is kind of Q. That is not a, our variation is in temperature and heat flux is Q. So it's a kind of what derivative of temperature in a sense. If you are going for a Fourier heat equation, the heat flux is in the derivative of a temperature. So heat flux, this cannot be possible in any end. So from here itself, the options uh, first A and D will be eliminated. Then the other two, what this only options left is B and C. Here in B, again the third one, that is heat flux and temperature at one end. So here they are only speaking about one end. So the other end is not specified. So again, that cannot be possible. The only option we have left with is C, option C. That is the right answer. We can have temperature at both ends. Suppose we are having a high temperature, suppose 100 degree at one and 10 at the other. After some time, we can expect the rod to have a steady state, to reach a steady state that it can have a distribution ranging from 100 to 10. So temperature at both ends can be possible. And also heat flux at one end and temperature on the other end. Suppose here 100 degrees there and this side is insulated, that is heat flux or some Q is there. That condition is also possible. So our answer is solution is C. That is either the boundary condition temperature at both ends or the heat flux at one end and temperature at other end. But heat flux at both ends cannot be possible because we are not giving directly the value of parameter. Here the parameter or the quantity we are interested is temperature. So if we are giving heat flux at both ends, then the temperature or the parameter we are studying won't be having values at both ends. So such a boundary condition is not possible. Our solution is C. So here it's about approximation or the discretization of the equation. Here for the following formula, a good approximation for dou square u by dou y square at grid point ij. So from the first week video itself, you might have seen what's a grid and grid points. So here the question is to find a good approximation for dou square u by dou y square. So for this, this is a grid approximation. Uh, this is a structured grid that is delta y and delta x is having same dimensions or almost same dimensions. Here I have shown the index nodes and denote index values for the nodes. So suppose this is our node ij, how the neighboring cells will be. So I will be varying in x direction and j will be varying in y direction. So if you are considering this line, this middle line, so the j values will be uniform. That is the y is equal to a constant. This uh, y is equal to a constant or line parallel to x-axis will be having same j values. So here you can say here it is j for all the points. Here it is j plus 1 for all the points, and in bottommost line it is j minus 1 for all the points. Likewise, I will be uh, varying with x. So it will be having x is a constant. So lines parallel to y-axis. So here you can see I minus 1 will be for vertically for all. Here I will be same. Here I plus 1. So here we are taking this particular point ij So for this, we have to find the approximation for the equation dou square u by dou y square. One second. So for this, we can take Taylor series expansion. So here I have shown a Taylor series expansion for uh, three coordinates, x, y, z coordinates. Here we only have x and y. So for f of x plus delta x and y plus delta y and z plus delta z, it will be varying in this fashion. That is actually a series approximation. Suppose we are giving uh, a delta value or delta increment in x direction, y direction, z direction, how the value or how the value of the function of the parameter of the quantity will change. That can be approximated using Taylor series approximation to a desired extent of accuracy. Okay, excuse me, somebody's trying to join. Sorry for the interruptions. People are joining intermittently. That's why. Okay, so here for this uh, point, suppose I am taking uh, sorry, vertical variation and uh, vertical variation. Suppose this point and this point, because from u I j I can travel up and down. So I'm traveling in y because our question is in y direction, dou square u by dou y square. So I am taking, suppose I am traveling in plus and plus direction, plus y direction and minus y direction. So here in plus y direction, the point will be u I j plus 1, this point. That I can write as, with help of Taylor series, I can write as u I j plus dou u by dou y at I j into delta y plus dou square u by dou y square at I j into delta y square plus higher order terms. So the good thing about Taylor series expansion or any kind of numerical approximation schemes is that we can choose to the order of approximation we need. So here we are only interested up to the second order. So we are only going to that much. So in plus the y direction, this is the variation. Again, in negative y direction, u I j minus 1, we can write it as u of I j minus dou u by dou y at I j into delta y plus dou square u by dou y square at I j into delta y square, and this will be minus. The minus will be alternating here. Sorry. And suppose we are adding these two equations, then we will be having this one, because uh, here uij is in both equations, then it will be 2uij, and the left hand side, that is uh, uij plus 1 plus uij minus 1, that will be in the left hand side, and again 2 times uij, and this time the first order term will be cancelled because one is positive and the other one is negative, so it will get cancelled and the equation will become like this. From this, if we are taking out the value for dou square u by dou y square at ij, then it will be like this. That is dou square u by dou y square of ij is equal to u of ij plus 1 plus u of ij minus 1 minus 2 times the value of uij, the whole divided by 2 into delta y the whole square. and the delta y all square is a delta y is a geometrical value, actually the distance that's we are taking from the geometry delta y value. So that much distance. So our options were this one. Someone said SR is u the velocity in x direction. Usually u v w are the velocity in x y direction, right? Yes. Yeah. Indeed. But it's in a three-dimensional space. You can vary in x, y, and z direction. So here, the question is about how u is varying with respect to y direction. It can disperse. It's in a two-dimensional. If you are taking in uh, one dimensional thing, so you will be varying in x direction only. If you are taking a two dimensional space, you can vary in u and v as well. U and v, both of them can vary in x and y direction. If w is there, three dimensions are there, it can, unless it is specifically said. Suppose it's a one dimensional flow, that is, it is not spreading. Even it, because that's how the variation happens. We will be giving only u velocity. Suppose uh, uh, for a duct, you can think of a pipe flow, fully developed pipe flow. We will be giving only one dimensional u velocity only. But inside that pipe is actually a three-dimensional space. Inside that space, we are discretizing. If we are discretizing the circular region inside a cross section in a pipe, uh, the u can vary according to v, with respect to y and z. So that's why if you have studied this eigenvalue equation and all, you will be known that why dial the velocity profile is taking a parabolic shape when it is developed, in its developed condition inside a pipe flow. So here, you can see, uh, since it is in the y square, the denominator should be y square. So either it should be a or c. Let's see inside a and c. Here, j plus 2, ui j plus 2. We didn't have to go for j plus 2 because the power we are considering is only up to uh, what, second order, or even we have only gone for the symbol schemes. So this one is wrong because here it is discussed j plus 2, and again here j minus 1 I. So only our solution is none of the above. D becomes the solution. Okay, okay. So there are some questions in the chat. Sir, if it's changing in y and z, j and k is the component. Actually, we are not talking the I, j. What I am talking about, the I and j, is not about the components of uh, vector components. This is the grid points actually. Suppose we are taking the points. I have a rectangle space, and I am dividing it into what a small rectangles inside the that given two-dimensional space. So as you can see, this space is geometrical space. Suppose you have a geometry and you need the geometrical properties. This delta x and delta y comes from the geometrical properties. Suppose you have a uh, uh, take the example of the problem, first rectangular duct. You have a rectangular space. So that rectangular two-dimensional space is being divided into small cells. So there, that small cells are not points. I am geometrically or spatially, I am calling it as I and j. So it is not the uh, vector denomination ijk coordinates in the vector. So these are what denomination for the spatial components, spatial points. I have a rectangular. Suppose I have a rectangular duct, and I am dividing this space into smaller regions. So these smaller regions, this thing is called meshing or discretization. The some one point, this point, how I can denote this point? Suppose I am calling it two, and this is one. So how I can call it? How I could name it in a, using this index notations. That's what I have done with this INJ. It is not the IJK component. I hope you understood the point. So moving to next question.
Sir, can I ask something?
Yes.
In the previous slide, can you just move it back?
Yeah.
Yes, in response to someone question that why we are not considering two factorial term, because that should be there in the Taylor series expansion. And since this is a central difference, so it will be like the denominator shouldn't have that 2 included. It would be only delta y square in the denominator, because that 2 factorial term is not present in the Taylor series expansion, as I can see in the slide.
Okay. As you have noted, pointed out, there was some mistake in the last slide. Let me correct you. Let's start with what's the Taylor series. So suppose f of x is a continuously differentiable function, then we can use Taylor series to expand f of x. So the f of x should be a continuously differentiable function, and then Taylor series can be used to expand f of x uh, at around some point uh, x is equal to xi. The Taylor series expansion I have shown the previous slide for three coordinates x, y, z. Suppose now we are only considering one. Let us consider a single point. I mean a linear mesh, one-dimensional mesh. Suppose let us consider a one-dimensional mesh. So this is the point I. This is I plus one, and oh sorry, this is I minus one. Since it is a backward point, it's I minus one. This is I plus one. So this is a 3 point. Consider these 3 points. For let first instance, let x is equal to xi. Then the Fourier expansion for that becomes f of xi plus x minus xi into dou f by dou x at I plus x minus xi the whole square by 2 factorial into dou square f by dou x square at I plus etc. And this is a general term actually. X minus xi the whole raised to n by n factorial into dou raised to n of f by x raised to n at I plus the higher order terms, whichever is higher terms than n. Okay, if we are applying this at I plus one point, that is here it was uh, applied at we expansion we used at ith point. Suppose we are taking it I plus one. So here x is equal to x I plus one. So we are simply changing this x here to x of I plus one. So the new expression will be f of xi plus x becomes x I plus 1. So x I plus 1 minus xi of dou f by dou x at I plus x I plus 1 minus xi the whole square by 2 factorial into dou square f by dou x square of at I plus h. Suppose if we are using that at x is equal to x I minus 1. So again we are substituting the x as x I minus 1. So here f of xi is equal to f of x I minus 1 is equal to f of xi plus xi minus. That is we are going backward direction actually. This not backward direction. This point we are considering this point, not backward. Sorry. So f of x I minus 1 is equal to f of xi plus x I minus 1 minus xi into dou f by dou x at I. Again x I minus 1 minus xi the whole square by 2 factorial dou square f by dou x square at I plus higher order terms. So let us call these two equation uh, 1 and equation 2. Suppose I am rearranging the terms in equation 1. So here f of x I plus 1 is equal to f of xi plus xi plus 1 minus x of I into dou f by dou x. So if we are rearranging it, then this dou f by dou x at I, we can write it as f of I plus 1 minus f of I. I am taking this term to the other side divided by the x I plus 1 by xi. The what is the multiple along with the dou f by dou x. And again, if I am dividing here xi plus 1 by xi, so the square goes and becomes xi plus 1 minus xi by 2 into dou square f by dou x square plus h. Likewise, if I am taking the second equation 2, and rearranges, then again the dou f by dou x at I becomes, sorry, this one here. Okay, carry forward to this page. So rearranging equation 1, rearranging on equation 1 will give us dou f by dou x at I is equal to f of I plus 1 minus f of I by x I plus 1 minus xi minus xi plus 1 minus xi by 2. So the square terms when dividing by this term throughout, the square uh, uh, the square term here goes and reduces to unity x. So xi plus 1 minus xi by 2 dou square f by dou x square plus h. That's higher order term. This we can rewrite as this. We are taking here delta xi for a uniform grid. We can take xi plus 1 minus xi. So the distance between the point I and I plus 1 I am taking as delta x uniform. If the mesh is uniform, the all the distance will be delta x. So it is delta xi. So I am substituting for this term. So it becomes f of I plus 1 minus f of I by delta xi. And this term I am taking it as order of delta x. So this is the terms we are neglecting. The terms from delta x we are neglecting. So likewise, equation 2 can be reduced to this one, f of I minus f of I minus 1 by delta x I minus 1 plus order of term, because we are considering towards the left side, it becomes out of delta x I minus 1. That times becomes. So these two equation, the first equation, I mean the result we got from equation 1, it is called forward difference equation, forward difference scheme, and this is backward difference scheme, these two. And if we are subtracting between these two equations, then it will give us this equation, this forward difference and backward difference. If we are subtracting from one another, then it will become like this: f of I plus 1 minus f of I minus 1, because f of I is common in both terms, it will get cancelled and only f of I plus 1 and I minus 1 remains. Similarly, x of I plus 1 and x of I minus 1 remains. But actually, x of I plus 1 minus x of I minus 1 means twice the delta x, this one, total length. So the twice the delta x, that we can rewrite as here. So this one is called a central differencing scheme, or central differencing using Taylor's series expansion. So this is of first order actually. So for a second order, we have to use the equations that we got from first order to go for the second order. So for dou square f by dou x square, similarly, what we have using a forward differencing scheme here, it becomes dou f by dou x at I plus 1, because this is actually what uh, dou by dou x of dou f by dou x at I. So I am just replacing that f by dou x. So it becomes dou f by dou x at I plus 1 minus dou f by dou x at I. I am just replacing f with dou by dou x. Then substituting the actual the values what we have found for dou f by dou x at I plus 1 and I, the schemes, the two schemes what we have found uh, just now, then the equation becomes like we are just substituting for these ones, and after cross multiplication and simplification, it will become like this. So here again, if we are taking what uniform grid, then it will become delta x, and substituting these as delta x, this also delta x. The final results what we are getting is this one. So dou square f by dou x square is f of I plus 1 plus f of I minus 1 minus 2fi by delta x the whole square. Okay. Again, this delta x is a numerical value, actually the distance between two nodes. So this is what we are getting from getting the value for dou square f by dou x square by neglecting the order of delta x square times. Before we uh, what sorry delta x the whole square times. In the previous slide, we just ignored out of delta x. Here, for a second order, we will be neglecting the orders of delta x the whole square. So in our problem, or in our problem, it was for y actually. What we have found is for x. What we imagined a one-dimensional mesh with 3 points. Here actually it's a two-dimensional mesh. So the question was, what is the point? What is the value for, or the discretist equation for dou square u by dou y square at point ij? So this is the central point. So at ij, so here if I am substituting uh, u for f, the equation becomes also, when it becomes in a two-dimensional, f of I plus 1. I is for x direction, uh, j is for y direction. So I have to take I, comma, j plus 1, because here you can see the denominator is y. So the incrementing is in what? Y direction. So the same procedure. I am just rewriting the terms. For f I minus 1 becomes u I comma j minus 1, because we are not incrementing in x direction, only in y direction. So I remains the same, minus 2 uij, the point where we have to find y. But here the delta x becomes, here it becomes delta y the whole square. So in our four choices, uh, none of the options, none of the three options was correct. So we have to go with the last option, D.
Okay, the next question is consider a steady developing laminar flow in a circular pipe. Which is of the following statement is true for this flow? Here, what is asked is for a steady. Uh, Understand the term. It's not the term developing. It's not a developed flow. It's a developing flow. Laminar flow in a circular pipe. And which of the uh, statements are true? So first statement is velocity profile changes axially. Second one is velocity profile changes radially. Third one is pressure varies linearly in the axial direction. Then pressure remains constant. So what will it be? I have shown here a pipe, uh, flow entering a pipe. Suppose this is some tank or some area from where the flow is entering, or some from somewhere it is getting into a pipe. So it will take some length to get it fully developed. So developing means it is yet to be developed. So it is in uh, it haven't got the spatial distribution of velocity haven't not reached yet. So that means the spatial distribution of velocity haven't reached it means it the velocity profile can change axially. And also spatial means both in x and I mean in x and r directions. So it can the profile change velocity profile can change axially as well as radially. So 1 and 2 should be the answer. And pressure varies linearly. This one is the linear variation of pressure in axial direction is a characteristic of developed flow. Here you can see. Pressure remains constant. That cannot be possible. If the pressure remains constant, then the flow won't be there. So the answer is option uh, A. That is 192. That is velocity profile is changing in both the dimensions. Next one. Consider one-dimensional flow governed by uh, dou square u by dou y square is equal to a constant over a height h. The interval h is divided into 30 equal segments. The upper walls moves to the right at a speed of 1 meter per second, while the lower wall is stationary. The number of discretized equations are. So here is it is taken for a one-dimensional flow, and it is in a vertical manner. So here, suppose this is the vertical discretized uh, length. Our boundary condition is the top wall is moving at 1 meter per second, and the lower wall is, or the bottom wall is at zero velocity. So here, if I am displaying in a vertical manner, then for n segments, there will be n plus 1 points, including the boundary points. That you may have been learned from the uh, discretization from the first week videos. So for n segments, suppose I want n segment, then the total number of nodes, that is discretized points, will be n plus 1. So for 30 segments, there will be 31 points. From that, our question is the number of discretized equations are. So in which all nodes we need discretized equations to find the value. So here you can see the total number is n plus 1, that is 31. Here in first one, that is the boundary node. So first one, the value we know, that is the velocity is u is equal to 0. So there we don't be needing any discretized equations to find the value. Again, in the last cell, that's another boundary condition. The velocity is again given if the top plate is moving in 1 meter per second. So there also we won't be needing any discretized equation. We don't have to discretize an equation there to find the value that is given. So these 2 points we already know. So from 31 points we know 2 points. So the points in between the boundary condition, we need discretized equations to find the value. So the answer will be 31 minus 2, that is 29. Here the option is 29, that is A. Next one, the correct equation governing flow in a fully developed uh, flow through a rectangular duct. So this also has been discussed in the first week's video.
Okay, the question was to find the equation for a flow through a fully developed flow in a rectangular duct. So this is the uh, momentum uh, x momentum equation. So general equation. So in the previous question, we have seen how a fully developed flow is different from a developing flow. So once the flow, even in a circular uh, pipe or round pipe, once the flow is fully developed, it attains a parabolic profile. So it is actually the velocity is only varying in radial directions. So like this, here if you see once the flow is fully developed, then it's the steady flow. So then the transient term won't be there; it will be 0. Then again for a rectangle duct, in normal rectangle duct by convention. So we take this as the x direction, y, z. So this length of the rectangle duct is in x direction. So actually the cross section will be a section of yz plane. So the like what I said earlier, it becomes a function in a round pipe. It becomes a function of r only. Here it will become a function in this the velocity is varying in this cross section only. It's a function of y and z. So it doesn't have any variation in x once the flow is fully developed. Okay. So till it is fully developed, the flow, as you have seen in the circular cross-section pipe, the flow becomes it will be a rectangular in shape in first. The velocity profile will be in a rectangular shape in first. It will be gradually attaining a shape of a parabola. Like after that, once it is fully developed, it won't be changing with respect to x direction or x. So u is for a fully developed flow, the u is a function of y and z only. So here dou u by dou x. So when it doesn't have any x components, it is a constant with respect to x. So this term becomes 0. And again, here we are only considering axial flow, only flow in one direction. So there won't be any v velocity and w velocity. So this becomes 0. This becomes 0. So entire LHS becomes 0. Left hand side. I have understood. So this all this term becomes 0. So in this step, this is the pressure gradient. That's what drives the flow. And this term is body term. Again, we are neglecting this body term for convenience. Then the equation reduces to this one. 0 is equal to minus dp by dx, which is the pressure gradient, plus mu into dou square u by dou x square. Sorry, dou y square. Because again here this term will become 0 as u is a function of y and z only. So once dou u by dou x is 0, dou square u by dou x square is also 0. So dou square u by dou y square plus dou square u by dou z square. Rearranging, we are taking this dp minus dp by dx to the other side, so it becomes positive, and also we are dividing with mu there. So the equation becomes this dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dp by dx. So that is the second option.
That here is given in second option. That is option B. Next one. I hope any doubts. Let me check. Okay, someone has said the slides are not changing. Is it changing now? For everybody, it's fine now. Okay, thank you. Okay, next question. Consider a fully developed laminar flow through a square duct of side L and through a rectangular duct width to height ratio of 2 such that both of them have same cross-sectional area. If the same fluids flow both the ducts at the same volumetric flow, which of the following statement is true about the flows? The options are the governing partial differential equation is the same. Second one, the wall boundary conditions are same though these are applied at different locations. And the third one, the flow domain is same. So here, uh, here it is said that we have two ducts. One is a square duct, the other one is a rectangular duct. The square duct has its side as L, and the rectangle duct has um, height to width ratio by 2. Suppose we are taking it is equal to square duct, then one side will be L and it will be the other side will be double 2L. So then the area, um, what the cross sectional area of the square and rectangle will be changed. So there, then since the cross sectional area is different, the entire volume will be different. The duct, suppose we are multiplying into the length, I mean uh, throughout the area which is fluid is passing, the volume will be different. That is, the flow domain will be different. So this is not true because once the cross section changes, the flow domain changes. Apart from that, the governing partial differential equation is same because for both of them, it is given as fully developed laminar flow. So the partial PDEs for the both the cases will be the same. We don't have to change it. And also boundary conditions also will be almost similar. So the option will be 1 and 2, that is C. This one. Okay, so here one case have been given. The some A few questions coming after this one will be taking centered on this scenario. So here you wish to solve a problem involving steady state conduction with a source term. In the case of fundamental flow, this takes the form k into d square t by dx square is equal to q, where k is the thermal conductivity of the material, t is the temperature, q is the volumetric heat generation rate. For this case, answer the following questions. So first question is that for equation 1 to be dimensionally consistent, the units of q should be, what should be the units of q? So this is a basic question. Here we know K is the conductivity. Conductivity, the unit SI unit for conductivity is watts per meter Kelvin, and temperature we are taking it in Kelvin, and also X in meters. When we substitute this and multiplying, we will be getting Kelvin and Kelvin will be cancelled. Then this meter square and meter get multiplied to get meter cube. The answer is watt per meter cube, and we know watt is joule per second. So the answer will be joule per second meter cube. So the answer is last one, option D. Next question. For the equation 1 to be one dimensional, the time q can be of which form? Uh, the options are q can be a constant, q can be varying in x direction, q can vary with respect to time, q can vary with respect to time and x direction. So here, if we go and check there, in this side, we don't have any mention of units of time. I mean, mention of time here. So the options including time, q, how we don't know how we can connect q to time. Just what the equation gives is joule per second. That is per unit time. It is our devoid of time. So these, hence we can't take these two, q of t and q of x comma t. Both these cases we can't consider. We can consider either q is a constant or q varies with respect to x. So our option becomes 1 on 2. That is option A. Which of the following is an admissible extension for the equation 1 to study heat conduction in 2 dimensions? So here, i- if you want to solve the equation in two dimension uh, without a transient term or the time varying term, we should have a value this change. So this for this we should get a constant time on the right hand side. So q of xy is like q will be varying um, uh, with respect to x and y. Q is varying. Then it is not a steady state condition. To get a steady state condition, we should have a constant value at the right hand side. So the answer becomes B. The next one, a client has produced a new catalyst that would improve the rate of catalytic chemical reaction and wants you to check it out using CFD simulations. For this problem, which of the following statement is true? This one I will give you time to answer. You can either turn on the mic and answer, or you can just put it in the chat box.
So could you repeat what you said right now?
I said this question, a client, I will give you time to answer this question. I was monotonously talking continuously. So this is a basic question or just understanding based question. So I had read out the question and I was asking you to answer. You can either turn on your mics and answer, or actually this is a practice session. It's not like we are giving you some tutorial or something. Here you can ask your doubts and get your result. I mean, get your doubts cleared.
Okay.
That will help you in solving your assignments, actual assignments. So if the client has produced a
Okay,
new,
since the
yes,
can I say something if
yes,
it's okay?
yes, yes.
Yes. So in the question, it's written that that client wishes to improve the rate of catalytic chemical reaction. So if you are trying to improve the reaction, so we should be knowing what should be the initial rate. So that's why the reaction rate should be specified. Otherwise, like everything follows, like whether or not it includes chemical reaction or like any other source term, they are all included in the fundamental which we use in CFD, which we discretize in CFD and solve. So, like
Mhm.
option C and option D won't be there. Option A should have been there if the initial rate of the reaction was specified. So, based on that, we wish to improve that rate. And since that rate is not present, that is why option B should be the correct answer.
Anyways, the answer is here. But I was whatever you have said is true. Uh, B is the right answer because from my first question itself, I have told you that what we are kind of simulating something. We are solving some numerical equation uh, inside a clean environment. For that, we should know which equations or which uh, fundamental equation or the phenomenon, the governing equations to solve. And also in that governing equation, there will be having some fundamental properties of the fluid or the in CFD we are inherently dealing with fluids, so we should have be well thorough with the fluid properties because like compressibility terms, mu, viscosity, everything is there. So everything, all those terms we should be well aware of. Then only we can plug it in the equations and we can discretize the domain and solve it. So here it is said that the client has produced a new catalyst. So the new catalyst, some of the properties we don't know, we won't be knowing actually. So in such cases, we can't uh, check for a go for a CFD simulation right away, because it needs some for new things, new material properties. Everything should be produced from actual experimentations. When we have some certainty about the properties, material properties, and everything, and then only we can go for CFD or this simulation. The advantage of the CFD is that once we know this, we can use these properties of the fluid in different applications. Suppose this client has produced a new catalyst, and in that particular person has derived all the fundamental properties, all the properties of this catalyst. Everything is well recorded. Then we can use these properties to check what are the application of this catalyst, where all we can use this catalyst with the help of the governing equations, and all together with the physical properties. So here some of the physical properties is absent. That's why we cannot go for a CFD uh, simulation. Okay, I think one or two questions are answered. Thank you. Okay, next one. You wish to solve a set of linear algebraic equations written in the form of Ax is equal to B using Gauss-Seidel method. So this method will converge if which of the following conditions is satisfied. So here it's a pure math based questions. If you have gone the calculus and classes and all, you can answer it. Uh, Matrix A is non-singular, then spectral radius of A must be less than 1. Matrix A is irreducible and diagonally dominant. These are the three conditions in which all the cases we can solve the equation written in Ax is equal to B. So answer it's given as uh, C. Can anyone tell why it is?
Okay, so basically, when we use any matrix method, like be it Gauss serial or Gauss elimination, whatever be the method, first of all, we need to know if all those equations which we are solving using the matrix method, they are linearly independent. So a criteria to test for linear independence is that the matrix should be irreducible. Like option one also satisfies the criteria, because if the matrix is non-singular, it means that the matrix is linearly independent, because it if it was linearly dependent, like one of the equations can be expressed as a linear combination of the other equations, then the determinant of that matrix should be zero. So like non-singular matrix also satisfies the criteria, but there are no combination in the options that are given, so we have to leave one. And since the option C, which is number 3, that matrix A is irreducible, that encompasses the point in 1 that is given. And the second criteria is that it should be diagonally dominant, because in Gauss seidel what we see is that the diagonal element should have the largest value. So that's a criteria for solving the uh, Gauss seidel method. And also the spectral radius of A must be less than 1. This is not a relevant criteria, because like spectral radius of A means the largest value, the largest of the eigenvalues of that given matrix. There is no such criteria that it is less or greater than something. Rather, the diagonal element, that should be the single largest element in the entire matrix row in order for Gauss-Seidel method to converge. So that's why option C is the given correct answer.
Very true, very true. Thank you. So, see, what's your name? Sorry, may I know your name?
My name is Pranil Bhattacharya. I'm an
Okay,
undergraduate fourth year student.
yeah, thank you, Pranil. The whatever you have said is right. For Gauss-Seidel, the first thing is it should be diagonally dominant because we will be uh, reducing the equations in such that we are eliminating uh, some terms equation one by one, and then we will be having you might have gone, some of you have studied this Gauss-Seidel method, or we will be using this Gauss-Seidel method, TDMA, all those in the coming classes. So in this, the diagonal, first for most of the CFD schemes or this matrix uh, solution schemes, the diagonal element should be present actually. So the diagonal element should be present and it should be diagonally dominant. So this is a valid criteria for most of the matrix reduction techniques in that is used in CFD. And the other thing is matrix A should not be reducible. That is, it should be irreducible. So these two things. So this one is actually both are the same. Non-singular and irreducible is somewhat same. So as Pranil said, uh, this uh, there is no combinations of one and three. So this one is what? Sorry, the one and three is combination combined in the third option. So the option becomes three. So the first one is actually when you are having a quiz or the exam. This is kind of a bait that if you see this is a non-singular, you know the for solving a is equal to b, it should be non-singular. You should be taking this one without reading the other options. You should be going for option A. You won't be having, and also the spectral radius. That term here, that's you might know how to tackle this multiple choice questions, but still I am giving you something. The spectral radius, all those terms may not be. Some of you might not be knowing what is the spectral radius. As Pranit said, it is the largest value among the eigenvalues. So for actually the spectral radius and all those things has relevance, but not exactly in our CFD or Gauss-Seidel method. So once we are going for the photicity and all those things, higher terms and all those things, they have some significance. And apart from that, it is in uh, electromagnetic and all those things. Spectral radius have much more relevance. But here, in especially in Gauss-Seidel method, spectral radius doesn't have any significance. So that is to just to lose your presence of mind. That's how the multiple objective questions are. So the third one, that is matrix A is reducible and diagonally dominant. That is the answer. And next one, an ideal fluid. I hope uh, you can give me answer. Anyways, the answer is still there, but I hope some of you can interact why. Why or what is an ideal fluid?
So, like it's option C because we know that ideal fluid is characterized by its incompressibility. Second is that the flow is inviscid, that is, it's non-viscous. That is why the flow is irrotational, that the flow is smooth and that turbulence is not encountered. It's smooth flow. So no eddies are located in ideal fluid, and that velocity also follows a steady state profile, that it's constant with respect to time at every point. So amongst those properties, option C is the one that satisfies that it is inviscid, that is, it has zero viscosity.
Okay, thank you. Again, here also, the question is about ideal fluid, but the first option what was given is ideal gas law. So the people will be thinking like gas is also fluid, so obviously ideal gas flow. That's kind of some skewed logic. People can at exam pressure can take the best of the students. So here for an ideal fluid, the answer is it should be inviscid, right? It should not have any viscosity. So an ideal fluid is called an inviscid fluid. So answer becomes C. Next one, an example for Newtonian fluid. So anybody explain can is what's a Newtonian fluid?
It is something that follows Newton's law of viscosity, that is, its shear stress, that is, shear force per unit area, is directly proportional to this shearing rate, that is, its velocity gradient at any point. So, amongst all those fluids, like every single one of them is a Newtonian fluid. So, it's option D.
Okay. Thank you again, Pranil. So mostly, again, this air, the values are much less for the viscosity. So air, mercury, glycerin, all these are for the but general purposes or general consideration. We are taking it as Newtonian fluid. That too, this Newtonian fluid, whatever he told is true. But again, these all things becomes in what domain, in what space. I mean, what is the dimensions where it can be treated as Newtonian. That's also a matter actually. But for general purpose calculation and all those things, we consider all these are Newtonian fluids. Next one, boundary layer approximation applies to. So we know when the fluid is interacting with the solid surface, there is something called a boundary layer develops because uh, the fluid will be the fluid layer which is near to the boundary will be having or will be uh, having a constant contact with the solid boundary. So there some boundary condition will be taking as no slip condition, that is the fluid layer which is in very close to boundary becomes uh, zero velocity or it will be stagnant, or having, but it is sticked with the boundary. So there, in such cases, there will be a gradual variation of velocities from the boundary or solid boundary to the free stream velocity. So that portion is called a boundary layer. So where this boundary layer flow occurs, that's the question. So the options are only to very low Reynolds numbers. Second one, only to high Reynolds numbers, but still laminar flows. The third one, turbulent flows. So for very low Reynolds numbers, such as the flow velocities for very much lows, the boundary layer approximation, because we don't have to approximate the boundary layer. The boundary layer will be so large in very low Reynolds numbers. Uh, and also in where we need to approximate the boundary layer, that much area or that much portion we have to approximate somehow to calculate the flow properties in the other region. So we need approximate this boundary layer property should be approximated in turbulent flows, also in laminar high Reynolds number laminar flows. The options B and C is same. So I mean B and C both are same. I mean both are relevant. Then the option becomes D. Next question, which of the following contributes to the viscous drag in a flow over a sphere? This is a classic problem in fluid mechanics. Sphere or cylinder? What is the factors that affects the viscous drag in a over a sphere? Suppose the fluid is flowing towards the sphere. Uh, Actually, what it happens is the area reduction happens because the presence of this sphere, the area reduction happens. The fluid has to here the area reduces. Suppose our domain take imagine it as some here these two, because to limit our vicinity, I am drawing two walls. Suppose so the fluid flow. The area, what happens here is it is kind of reducing the area because of this presence of the sphere. The area is reduced. So this portion, if you consider this one portion, either side of the portion, it will act as some kind of convergent divergent nozzle kind of thing. Not exactly, but somewhat. It will be converge for the first. The area reduces and then it enlarges. In such cases, the pressure variation seriously plays a role, and also the what how the shear stresses developed over this surface. This will also has a say on the viscous drag because drag is due to shear the flow over the sphere. How the flow interacts with the sphere surface. So it's the outcome of shear actually. So wall shear and also the pressure variation. So why the pressure variation comes into picture is like is and actually what happening here is the area is reduced. So you know how the pressure will vary when the flow area is reduced. So once such questions like this over a sphere, over a cylinder or something, you try to imagine there is some bounding, there is some layers, some walls restricting here. So then you will understand how what is happening here. Actually, the fluid has to skews itself to the area available to flow. So both the wall shear and pressure variation will have a say on viscous drag over a flow or a sphere. So the options become option C. Next one, in laminar fully developed flow through a pipe, the axial pressure variation is linear. The question is, in a laminar fully developed flow through a pipe, what will happen to the pressure? Option A is axial pressure variation is linear. Second one, radial pressure profile is linear. Then radial pressure profile is parabolic. Fourth one, pressure is constant. Axial pressure variation is linear. That is the option first. Option A is the answer. Axial pressure variation is linear. That we have discussed. Yes, here. So this is a fully developed flow region. Here you can see the pressure varies in a linear fashion. So this one is the answer. Axial pressure variation is in linear. So radial because there will be how much radial pressure variation. You can't say pressure variation is linear, and also it won't be parabolic. If the pressure is constant, then the flow won't happen actually. The driving force is actually the difference in pressure. Next one, in steady incompressible flow through a converging diverging nozzle, the pressure at the exit section is. So the uh, options are highest, lowest, lower than the inlet, same as the inlet. So if the pressure is same as the pressure at the exit is same as the inlet, then there won't be a flow actually. Then converging diverging nozzle. So you know how the pressure will increase and decrease. So you can't say it will be the lowest. So uh, it won't be the highest also. And once it is passed to a converging diverging nozzle, there will be some head losses to the flow. Then you can say definitely you can say that is it will be the pressure will be lesser than that of the inlet. So option is C. Next one, over 50% of the time spent in industry of CFD projects is devoted to the definition of the domain, geometry, and grid generation. Which one of the following will be the reason for this? Uh, Options are more grids will give better results. Option 2, calculation time is directly proportional to the number of cells. Third one, to generate non-uniform grids. Fourth one, to generate an optimal grid, which is compromise between desired accuracy and solution cost. So, the answer is fourth one. Can you say why it is? Anyone?
Okay, so if we increase number of grids, what will happen is that our accuracy will increase, because then we'll be able to, like, since finite element methods are generally used in CFD, so we evaluate partial derivatives or derivatives in general. So the smaller our grid spacing will be, the greater will be the accuracy, because we are approximating derivatives. So it means an infinitesimally small spacing between 2 points. So that is why our accuracy will increase. But on the other hand, what will happen is that we are discretizing into a lot of algebraic equations for each of the grid points, and then we are totally solving that all of those algebraic equations using matrix methods, or like factorization of matrices, to get the solution vectors of our desired variables. So what will happen is that our computational time will increase drastically, like the amount by which we increase the grid spacing. So thus we need to like optimize between these two opposing constraints, and then find what should be the optimal grid spacing. So that's why it's option D.
Okay. Do anyone know for this thing? If you are doing, we have a new geometry in our hand. So how can we reach such an optimal grid? So there,
We do that grid generation test, like something like that. We check for different values that come with different changing sizes of grids, and once we come to one grid where the desired value is not changing with while we are changing the grid spacing, that is our optimal grid. That we generally do that grid generation test, or something like that.
it's called grid independency test. So,
Yes, grid independency test. Yeah, I forgot that name.
okay. So it's called an grid independency test. And do you think this uh, grid independency it will be in industries? Do you think it will be run for every new geometry? Asking in the industrial level. Suppose you are working in industry and you have to like you have to check different manifolds, intake air intake manifolds. Newer designs are coming to you every day. So will you be doing grid independency study for every geometry you are getting?
It will be very like computationally expensive procedure, like doing so many tests.
Mm.
Okay, actually, I don't know if you know this. Even for weather forecasting, suppose some hurricane is passing through some region, this hurricane forecast, all those things, CFD is used. So in such cases, if you are going to, you can imagine how large the number of cells will be. But that is one thing. But here it's specifically said industry. So in industry, actually even the grid independency test won't be. They will do only the grid independency test when it is very much needed. Apart from that, if suppose they will be having some rule of thumb or some geometry or some range of geometry or the Actually, this how one question again. How do you think the meshes are varied? I mean, this different. How are we supposed to generate different mesh or different grids? What you will be defining?
We shall be defining the shape of the grid which we are using, say triangular mesh or square mesh, and then we alter with the dimension of that mesh, and thereby we see how many meshes are fitting inside the geometry.
Yeah. Okay. Then again, this uh, uh, if we have to what split the CFD entire CFD process into two, the large chunk or the equal chunk will be grid generation or geometry specific thing. Because what we need is geometrical values. We need uh, the distance. Suppose I have showed you in the first few slides this delta x and delta y. Here, this delta x, delta y, this in this discrimination, this delta y and delta x, these two values are actually geometrical parameters. When you can imagine, suppose it is in a triangular duct or some irregular shape, there this delta x and delta y and also this equally spaced grid points won't be there. So this delta x and delta y will be varying, or also if there is delta z also in a three-dimensional case, all these quantities will be varying. So how to generate a mesh? What I have shown is a equally spaced structured mesh. So you said triangular elements or triangular or such elements, tetrahedral elements. There are different kind of elements that can be used for meshing or discretizing. This is actually entirely geometrical thing. How we are reducing the geometry to apply our what approximation of equations. So meshing is one important thing where we are reducing the geometry. So my question is, why do we need uh, this geometry to be reduced into more number of cells? Why we are going for lower, lesser, and or maximum number of points?
Because like the intervals, because the element length, that is the distance between two nodes or vertices of our geometry, that as it is being decreased, that means our derivative is better approximated. But say like I have one variable u, and the PDE for that contains a del u del y term. So that means, in if we are doing looking it from an ideal perspective, let's say the analytical perspective, there del y represents an infinitesimally small spacing between two points, because limit y tending to 0, that infinitesimally small spacing. So like in order to increase that level of accuracy, we need as small as possible interval length, so that our partial derivative equation that we are approximating over that interval, that gives us an accurate measure, so that like the change, the nonlinear change in any quantity, that is not captured much in our PDE. Like we approximate, because like the smaller our spacing is, the nonlinear nature of the function, that we capture only the linear part of that function, and that's why we can use that formula dy dt and calculate the derivative at that particular point. So in order to like better um, approximate that, and with greater accuracy we want to approximate a derivative term, we need the change in the independent variable as small as possible. So that is why we need small intervals in our constructed geometry of grids, and that's why our number of grids should be increasing, because grids will be smaller in size now.
Uh, so what you have said is true. For others, I will make it somewhat simpler. So there in the equations, we were converting the uh, partial differential equations to numerical approximations. So the del x I mean, dou x, dou y, all those terms were continuous terms where uh, those terms doesn't have any limit. Actually, you can't put a limit to that dou. So when you are converting that dou to del x, that del is something that can be measured, or that should be what matching the geometrical. I mean, it should capture the variation of your particular property. Suppose you are studying this velocity variation. So the velocity variation in the particular geometry you have should be what able to be captured by that del x and del y. Suppose it's like you are using a net to catch a fish. If uh, the mesh size is too large, it can slip through, and making it uh, too small, the mesh size too small, actually it is irrelevant. If we are going for, it's an overkill. So we need our mesh size, that del x, del y, all those uh, value should be almost in terms with the variations of the property we are studying. So that's why the term optimal grid comes. So suppose it's not like we are reducing the del x del y uh, to a lower values, then the number of grid elements will be much more higher. And if you are keep on increasing the number of cells, it is not likely that you will be getting the you are keep on getting good results. It's not like that. Like the catching fish example, beyond some level, it won't give some because what once that particular variations can be captured by your del x and del y, uh, uh, further decreasing del x and del y won't be helping because you will be getting similar results. Then uh, even we won't be going to that much also, but we will be going to how to a portion where it retards, like how the change in the suppose I have a mesh with 2 lakh nodes, and then I have reduced the delta x and delta y values, then I will be getting some 5 lakh mesh, then again a 10 lakh mesh, and I will be comparing this results of this 2 lakh mesh with the 5 lakh and 5 lakh with the 10 lakh. And if I am plotting the number of cells to that particular change in value, you'll be seeing that the curve is almost getting a flatter because there won't be a change. Initially, there will be a change in the parameter you are studying, value of the parameter, but after reaching some certain value, even you increase further, the number of cells are increased further, there won't be much variation in the studied value or the parameter which you are studying. So we will be taking some as the we can fix. I told you, CFD's kind of approximation. We can choose the accuracy. We don't even have to go to the flatter region itself. We can say, okay, this much variation, this much uh, error is acceptable in my calculation. So in that particular, suppose 10%, 20%, or 3% errors, what is your what you can handle. If you are reached that much level, then you can fix it. So that's an optimal grid. So grid independency study is what I told you now. We will be increasing the number of mesh elements for the particular given geometry, and we will be doing CFD calculations again and again. We will be comparing the results of one grid to the next grid, and once we are seeing there is no variation in the results or minimal variation uh, in the results, then we will be fixing the uh, second last grid as our grid to follow. So that particular study is called grid independency study. So and also you will be seeing in most of the CFD thing, CFD courses, we will be going for the discretization of the equation, but the geometry meshing of the geometry is entirely a another thing where you know how to you have to understand how to divide the space, or if it is a 2D space, you can be divided with the square cells, rectangle cells, triangle cells, which will give the better results. All such thing is a entirely different branch of study from the geometrical perspective. So both are relevant in the CFD calculation. That was my point was. So here the option D is the right answer. Next question: in a turbulent flow through a rectangle channel, if the flow rate is doubled, then the pressure gradient is likely to uh, remain the same, double, quadruple, be 16 times higher.
We can solve this using Darcy Weisbach equation or Fanning equation, and from that we can see that pressure gradient will quadruple.
Yeah, pressure gradient, because pressure gradient is directly proportional to V square. If you are
Yeah.
uh, uh, doubling the rate, then it will be 4 times. So the answer is quadruple. Okay, that's all thing. I've run out of my questions. If you have any doubts, you can ask.
Sir, I want to know the final conclusion regarding that question 3 discussion, the factorial one.
Okay, I
Uh,
will change that. I have to check again actually.
okay.
I will this slides you will get. You can access these slides as well as this uh, video
Can
will be
you,
uploaded in YouTube.
because in week one lecture there will I gone through that week one lecture. There is no two there in delta x delta y square in denominator.
Sorry,
So
I didn't get you. Uh, can you come
in
again?
week one lecture,
Yeah.
I went through that week one lecture. In all the lectures in equation in algebraic equation, there is no two in denominator. So that's why I confused actually.
Okay. I will check again. Sorry for the
Okay,
inconvenience. I will check again and I will add that proper solution in the end of the video when I am uploading it in the YouTube and as well as in the PPT.
okay. Thank you.
Anything else? Any other doubts?